So if you see the cross section view of this one, so you will find that our structure is something like this. Here we have a substrate and these are our copper wire, copper conductors. So this is very similar to microstrip.
Sorry to interrupt you, sir. Hello,
Yes,
Muqaddar
sir.
sir. Your screen is not
Yes.
visible, sir.
Okay. Just give me a minute.
Yes, sure.
Vikram,
Yes, sir.
I think there is some
Is it
issue with
visible now?
Sorry, sir.
I think there is some issue with the YouTube.
No, YouTube is live, sir.
Okay. Fine. Okay. Yes, Muqaddar, you can continue.
Okay, so the screen is visible now.
Yeah, it's visible.
Okay, so now if we see, this is our waveguide structure, and these are this rows of wires to implement the sidewalls. So this is a waveguide that we have implemented. Now we want to connect it with our planar structure. So how we can do that? For doing that, we will be using, if we see the cross section, the top view on top, this is our, this is the top of your SIW. Now, when we have this feed line, this is a microstrip feed line, and its thickness will be lower than the width of this SIW. So how these two will match? So if you go through the uh, if you go through the mathematical models of this waveguide, then it will display the input impedance of this waveguide, that is the wave impedance, that comes out to be very high or very low depending on the width of this waveguide. So first we need to do, we need to go to the results and select the Z parameters at the port terminal. So click here, right click here, go to models, create a rectangular plot report, and here we see there is one parameter that is called port Z0. So this parameter displays the impedance of your input port. So at we have designed our antenna at 9.5 gigahertz. Now go to X marker and select at 9.5 gigahertz. The input impedance comes around to be 66 gigahertz. Okay, so this all depend on the width of this SIW, the distance between these two wire rows, and the height of this substrate. So if we change the height of the substrate from 1.5 to 2.0787 mm, and now we try to rerun this design, then we will observe that the input impedance has increased. Sorry, the input impedance will decrease. Okay. So now if we see the impedance that is in at port M2, this is 89 ohm, whereas earlier it was lower. So we in this case also in this case we will have to match the impedance again. But what I wanted to display, I wanted to show you this result. So as we see, in case of when we reduce the height of this, uh, we reduce the thickness of the substrate, then the impedance has lowered up to 34 ohm, and earlier it was 69 ohm. So now we the purpose of SIW is to have thin substrates. So we are designing this at 7.787 mm, and at this point we are having an impedance. The port impedance of this waveguide is 34 ohm. So now how do we connect our microstrip transmission line with this? So that is a challenge, and for that we have to design some uh, structures that are known as microstrip transitions. So what we will be doing, uh, So, in order to match, connect our 50 ohm microstrip transmission line with this SIW, we need to implement an impedance matching network in between these two, so that the length of this will be lambda g by 2. This the length of this transition section will be lambda g by 2, and the width of this section we will be determining based on the input impedance, or we can use trial and error methods. So let us go to the simple SIW that we earlier designed. This is, I think this was the design. Okay, so this is a simple SIW, and it we are feeding this SIW with wave ports, and if we check the impedance of these wave ports at port 1 and port 2, at both the ports, we observe that our SIW has higher impedance, 61 ohm, and whereas our feeding network will have an impedance of 50 ohm. So we need to apply a impedance matching technique here, and that we can apply a tapered transition. So in order to realize that, we will be going uh, from here. Let us set it to 0.787 mm. Then what we need to do, we need to extend this ground in both directions. So I will go to ground, then select here. I will start this ground from minus L F 1, and let us give it around 20 mm, and increase this length by 2 times LF. Okay. So now if we see, let us remove this one from now. So this is our ground plane, and the top layer I will change the color so it is visible. So our SIW is in this region only. Change the make it transparent. So now you can see these are the wire holes, and at this region we have the SIW and substrate. Let us change the substrate length also. So the substrate is also starting from minus LF1 to L plus 2 times LF1. Okay. So the substrate we have extended the ground, we have extended the substrate, and the top is on the SIW. Now what we need to do, we need to add a microstrip line. For half of the section we will add this microstrip line. Then from minus this, it is starting from minus LF1, and the thickness of this will be minus WC by 2. Sorry, the width of this microstrip line is WC by 2, and it will come around 1.4 mm, 1.45 mm, and the size will be WC, length is LF1, so LF2, and let us give it 5 mm. Okay. Now the thickness of copper is T, and it will start from H plus T. So now we have added a feeding and apply the material copper. Now let us connect this impedance transformer here, a tapered impedance transformer. For that I will be drawing that shape. So start with draw line and zoom in and select this point, connect this point to here, then here, you can take it roughly and change the shape later on. So when the starting and ending terminals of this polygon are same, then it closes itself. So this is the polyline, and these are the different edges that we have drawn. Now you see both the point starting and ending points were same, so it has connected. It has added a one operation, that is cover lines. So it has converted this into a sheet. So now we control this one, the width minus WC by 2, and it is starting from minus LF1 plus LF2. The Z points are H plus T. I will copy this one and paste here. So now I want it a triangular shape. So the starting point is 50 ohm. The ending point will be according to our impedance. So I will select it WC1, and let us say it is 2 mm. So now go to the next point. So here you can see that for the first line you have given both the points as variables. Then in the second line this was the first line. Okay, we made a mistake here. Double click here, and now it will be connected with the 0. So let us give it LF3. Okay, so LF3 I am giving it 8 mm. And I think minus WC1. Both these values were positive earlier. So now you can see this is the edge that we have created. Now for this edge, we have the starting point. Just copy this one, and in the x-axis I am giving it negative, so it becomes symmetric. Now go here. This is the fourth point, and on y-axis it is minus LF plus this one, and here it is minus WC. So this is the shape of our transition, microstrip to SIW transition, and we are going to make it a little bit more so it can be visible. So this is our SIW transition. And this one is our field. So here we can see that this one is a sheet and this one is a solid. So what we can do, we can select this one and go to thickness, thicken this sheet and give it T. So now it has also become a solid. Now what we need to do, we need to connect both of these. And now you can see this is our microstrip transmission line. This is our microstrip transmission line. Here we will be connecting a wave port. Up to this point, the length, the width of this microstrip line is corresponding to 50 ohm, and from here it is starting to flare. And at this edge, we have the impedance that is matching our waveguide impedance. Okay. So now we connect both of these, and this gap we will control by the LF. So LF1, this width was LF2, and this taper length is LF3. So we will make it LF1 plus, LF2 plus LF3. Okay. So now it has got attached SIW. Now what we need to do, we need to make a copy of this one. So just select this one and create a mirror copy along the y-axis. So this appears somewhat displaced. So select this mirror and make this position to 0, L by 2, 0, and the normal direction is 0, 1, 0. Okay. So we have put our mirror at the center of this SIW in XZ plane. So the Y plane, the normal position is 0, 1, 0, the Y axis, and we have put the mirror at L by 2 distance. So it is connected like this. Now what we need to do, we need to change the wave position of the wave ports. Earlier the wave ports were full here. So now we have created this from the surface of the substrate. So we delete this one. Now create a sheet, and from its properties, select this sheet. From its properties, set this to Y, and we will be starting W minus the W port by 2, and give the height we are starting from 0, so minus LF1 and 0. W port we are going to give it around 15 mm. Then in the x-axis the length is W port, and in y-axis it is H port. Okay, so the H port is around 8 mm. Now create a copy of this one, and set its length L to L plus LF1. So now we have connected both the ports here. So what we have done, we have created a SIW transmission line. Then from so here what we have done, we have created an SIW transmission line and connected this transmission line with a microstrip line, and this is the shape, overall shape. Now we connect both the box and the top. This will be connected. Now we have a complete top structure, and this one is our bottom structure here. So here you can see we are simply adding a tapered impedance transformer here, and the length of the tapered we will be calculating from the formula of the impedance line. Here we changed the length to 0.7, and the port impedance was around 34 ohm. And for calculating the impedance values, we go to EM top. There are several options available for calculating the impedance. From all about circuit or everything RF. Everything RF has a better option for calculating, and one more is there, that is EM top. So here we give our width in mm. So the thickness of this we are going to calculate. So the thickness we are giving 1.5 mm. The trace thickness is the thickness of copper, that is 0.007. The dielectric thickness is 0.787. Dielectric constant 4.4. Now if we calculate the impedance, it will display how it for 1.5 width of the microstrip transmission line, we are getting 49.1 mm. So we selected 1.45 mm, that is giving around 50.3 ohm impedance. So WC is, in this design, we set WC to 1.45. Then we were having around 35 ohm impedance of the, for the input port of waveguide. we need to calculate, and let us make it around 2 mm. So 2 mm is around 38. Further increase it 2.4 mm. So around 2.2 mm would be optimal. So WC1 we are going to set it 2.2 mm. Okay. Now how do we calculate the length of this? So for length we also we go to the port impedance and click here. Go to lambda. This will give us the guide wavelength at the port. So select this one, and at 9.4 we have around 37 mm. So for 37 by 4, we need to take this lambda g by 4. So we will be having around 9 mm of transmission. So LF2 we are making it 9.5 mm. And now if we simulate, I think I accidentally deleted the region. Add this one from region. We are adding wave port, so input minus y and plus y, we will be having 0 mm extension padding. Now go to isometric view, and this is our region. Okay, these so this is our region that is extending from minus LF1 to L plus LF1, and we select this region and apply the boundaries. Then we select this port 1 and apply the excitation to wave port, and okay, in order to design we need go here, select one, and fit this one. Now right click here and click excitation port, wave port. From wave port we will selecting this new line starting from 0 can only be created on a selected face. I think I accidentally selected multiple faces. Okay, this region is visible, so let us click this one. Now I have make this region invisible. Now when I I'm selecting this face, I'm only selecting rectangle 2. So right click here, go to port, wave port, and create a new line. Lines can only be created on selected faces. Okay. I think there is an issue with the zoom in problem. Okay. Okay, so earlier the issue was I was selecting the object. Instead of that, we need to select this face. Okay, so we have defined the wave mode for wave port 1. Then go to the backside, select this rectangle. Now right click, assign some excitation, click the port. So now it is finished. So So if we check all the things we have done so far, initially we have a ground plane that is extending from minus LF1 to L plus LF1. L was the length of our original wave SIW transmission line. We have a substrate. After the substrate, we have these cylindrical walls implemented for SIW. These are the side wall of the rectangular waveguide. And then we have this section is our waveguide section, SIW section, and we have a taper transition between the transmission lines. Now if we click validate all, there is no error here. Then click analyze all. Okay, so I think the simulation is completed. It is taking some time. So let me give you an example. If you see this structure, this WC is the 50 ohm transmission line, and this WT is the taper transmission line corresponding to the impedance matching for this one. So in my design, I was getting the wave port input wave port impedance of the SIW. I was getting higher than 50 mm. So that is why this WT is smaller than WC. Otherwise, if your impedance is smaller than 50 ohm, then you might be having WP. So here if we see here, this results, this is showing that there is a loss of 0.6 mm, 0.6 dB in the power for in the transmission coefficient, and otherwise the input signal is properly matching. And earlier this S11 was also less than 10 dB here. So because of this, what we can do, what we can optimize this LG as we calculated the length, the port impedance. The port impedance is around 67 ohm. Okay. That might be different. The wave port dimension. H port. So for H port, we normally take 5 times the height extension. So H, now we have H substrate is 0.7, so it will be around 5 mm the height, and the width will be 4 times the height of the substrate in both the directions. So the width we are going to use W port 5 times, so 336 8 mm. Okay, that will give us the right impedance. So now what I will be doing, we in order to measure at this height of 0.7, we need to take some extra step. So I will return back to original height 1.524 mm. At that height we had a proper matching. Now for this height I am going to calculate the impedance. That impedance is 66 ohm. So I will be matching that one. And now it looks something better. Still the impedance is there. So I think okay. I think I made a mistake for calculating this. I used dielectric FR4 instead of Rogers. For Rogers, the impedance is around 1.8 mm. So for Rogers, we will need a thickness of 2 mm, and for 35 ohm, we will be needing around 2.8 mm. One second. Okay. So when we update here, Now we will be getting the right impedance. Okay, so this time the impedance is around 50 mm. We were designing at 9 gigahertz. So here we are having around 55 ohms. So we can further tune these parameters. Then if we go to the electric field distribution, and so these are the electric field distribution, and we have created this sheet as a known model. So if we can extend this length, and now we have extended that sheet, and we can see that from port 1 the signal is being transmitted from the microstrip line. Here you can see the fringing fields, and this length that is extending far beyond. So I think we have uh, made this around lambda by 2 instead of lambda by 4. So we can reduce this one, and if we click here and animate this field, you will be able to see how the wave is propagating from SIW to from microstrip to SIW. And I think this I made a mistake here. This should be only lambda by 2, lambda by 4. Let us make LF2 as LF3 5. Because the lambda g that we calculated, that was inside the waveguide, but here we are not. The wave is not uh, went inside the waveguide here. So there is a difference between the wavelength. Now we see, now the return loss is much better. So in SIW, what happens? The uh, the length, this transition length that I said it should be lambda by 4. This transition length should be lambda by 4, but it will be only for a particular frequency, and for a wider frequency we are hoping that this taper transmission transition will give better frequency range, but we need to optimize this one further. So whenever you are designing the final antenna, you can optimize this uh, with WC2 and this length also. So based on your requirement, if you are operating in this frequency range which has very good impedance matching, it is okay. But if you are operating around this point, then you need to optimize this impedance transformer. Okay. So now, in order to design an SIW antenna, first we need to design the waveguide, and then we need to implement the SIW by using the wires. And after that, there are two approaches. Either you first design this microstrip to SIW transition, and uh, another approach is you can design the antenna first, then add the microstrip section. Okay, so now earlier we have designed this antenna, and it was having very good impedance matching. Now what we need to do, we need to match for this one. So the height of this was 1.5 to 4. So let me make this 1.5 to 4. In that case, we will be have to change the wave WT, sorry, the WC2 and WC1. So go to the calculator, 60 ohm. So for that, we will be having 1.6 mm width. So if we change the height and we change this WC1 to 1.6, click OK. So because we have increased the thickness of the substrate, the input input impedance of the SIW has come out to be higher. So because the input impedance is inversely proportional to the height of the substrate. Okay, so in order to apply, by the meantime, this design simulate, I will create a copy of this our antenna and paste this one. Now here I will extend the ground and substrate. So for ground, I will be starting from minus LF1 to LF1. Right now I am taking it 15 mm. I will change that later. And the length of this will L plus LF1. This will remain the exact same as earlier. Then we increase the substrate also. Okay. Then after increasing the substrate, now we will be connecting this with the wave port. So this wave port will change. Okay, so simulation is completed. Now if we see the matching, it is somewhat we can simulate with this one. And for if you want further improvement, you can tune the parameters. So I will select this one. Now go here. Select. So I'm selecting this one and paste the complete design. And remove unnecessary components. This we don't require. Now this is the transition, and here what we need to do, we need to change LF1. So LF1 is LF2 plus LF3. So now this transition section is added here, and if we go to the excitations, you see earlier we have connected a wave port at this point. Now we need to change that wave port. So we are going to place it at the microstrip end, minus LF1. The size of the wave port will be minus W port by 2. W port is around 9 mm. W port, and height is around H port. H port is around 8 mm. Now we simulate this design. So now you can see these are the results, and if we see the previous results, right click on this one and copy the data, not the definition, paste here. So now from here we can see that originally our antenna, the impedance the return loss of our antenna was this green button now, and now there is we can observe there is a slight shift in the frequency, and the impedance matching is also improving here. It is like making it a dual port mode. So why it is happening? If we see the Z parameters here, the real part of the impedance was around 70 ohm at this point, and it is in the range that it can be easily matched. So what we can do, we can also use this matching, this transition to further improve the bandwidth. But and so this is how you can design your matching network for SIW antennas. Now for the workshops, last topic, that was antenna array. We will be simulating an antenna array here. So that will not take much time because we have already designed an antenna earlier. So in our first lecture, we have designed several antennas. So I'm going to select this antenna in which we have designed this coaxial fed microstrip antenna, patch antenna. So if we go here and check the designs, okay, some of the results are missing. Let us redesign this one. So this is a direct feed microstrip patch antenna made up on FR4 material. Because of this, the results are mismatching. Okay, I made a duplicate of this one. So let us simulate this antenna. And, we made some tune. I think by mistake I made an error here. So accidentally I deleted the outer ground structure. That is why we are not getting the results. So I created a cylinder again for the outer conductor. Then I will be subtracting this cylinder to make this hollow. Now from top view you can see this is the outer conductor. And now if we try to simulate, it is giving error ground and cylinder 3 intersecting. Okay. Now since we have changed the geometry, because this ground conductor was connected with the port, so go back here at the bottom. From bottom we see this excitation. I think it got duplicated. Now select this one, this cylinder with this one. Now we will be assigning the wave port again because due to change geometric change in the face where we are adding the ports. If there are some changes, then we need to reassign the wave ports. Okay, again we are selecting the object. Now select the face, right click, go to excitation, ports, wave port. Now we will apply the boundaries. Now let's try to simulate this one. Okay, so we are getting the results now. The antenna is radiating around 2.4 gigahertz, and we want to make an array of this antenna. So what we need to do, we make a copy of this one, and I will add it in this one. So this was our design. Now let me close other projects. So in order to simulate an array of the antenna, what we need to do, we need to apply master and slave boundary conditions in our design. So there is a simple trick here. What we can do, we can select this whole antenna and select this region. And in this region, what we are going to do, we are going to uh, remove the padding in X and Y directions, because our antenna is placed in XY plane, and in Z direction we are keeping the padding. Let us make it 50, and in minus Z axis we are not removing the padding because we are using the waveport. Uh, so now it is the region is like this. It is touching the boundaries of our design antenna. Now from here, from this object, select this region and right click here, go to excitation, go to boundaries and go to coupled boundaries. Here we can apply the primary and secondary boundaries that will connect the phase, and we can also create lattice pairs. For example, we select this phase 1 and then we select the other phase. But there is, when we select this object and right click here, go to boundaries, then go to coupled and click here on auto identify lattice pairs. Okay, and our antenna is placed in XY plane in the global coordinate system. So click OK. Now check here in the boundaries, this radiation, we will remove this one. This was previous. Now you can see that there are two lattice pair boundaries are added, and these boundaries are selecting the opposite phases of the region. So this will work fine. Now at the top of this region we will apply the absorption boundary condition, the radiation, or you can apply perfect magnetic conductor boundary here. So PM instead of PML, I am selecting radiation boundary. Similarly, in the bottom also, we will select the phase and apply a boundary condition as radiation boundary. Uh, Give me 5 minutes. So now we have created a single patch antenna, and we have applied these lattice pair boundaries. So now our unit cell of the antenna array is completed. Now click on the analysis. Once the analysis results are there, then what we can do, we can identify the antenna array pattern of this one, because we have designed this antenna in such a way that we have applied the master slave boundary conditions here. And if we click here and double click on the lattice pair, then we can change this phase delay. Uh, so in 5x scan angle, we are giving a phase delay of 5 scan. In theta, we will be giving theta scan. Okay. That in that case, in that way, we can make these variables. Now the results are there. The simulation was deleted because of save. Okay. So the problem with this is it does not allow fast sweep. So I will change the sweep from interpolation, fast to interpolation, and clear the boundaries and simulate it again. Okay, so with interpolation results, those are some better results, and there is a slight change in the operating frequency. Now let us click here and okay, we forgot to add this radiation sphere. Now go here, check for the far field results, draw the polar plot, realized gain, total realized gain in dB, and from here I think it will display the result at the operating frequencies 2.3. So the results are present. Now we change this one, make it a depth sweep, and from the frequencies we have 2.3. Go to the sweep, select this frequency. Okay, still there are no results. So instead of this, change the sweep to district, and now we are going to have around 51 points, sorry, 21 points in the range 2.12 to 2.5. So in discrete mode, at every single frequency, it will recalculate the results. So we are going to use that. So I hope now the results are available. So this is the result for our antenna, and the total gain is around 0.5 dBi. Now, if we go here, right click on this infinite sphere, uh, right click on this one and compute. Uh, Here right click, and here we can set up in the near far field, we can also set up an antenna array setup. So make it a parametric array, then select the geometry. In the geometry, we will be giving the direction in x 0, y 0, and z 0. So in x and y, we can increase the number of antenna elements. And in the x vector, center position, array weights. Setup. I think this option is not available in the student version. So, alternatively, what we can do, we can go to 3D components, right click here, and Okay, so I think there is some error. I'm forgetting the steps here. So let me try this one. Go to tools. In tools, we might be getting go to HFSS and go to antenna toolkit. Then select this finite array beam angle and click this one. So we'll go here, change the solution type to hybrid and terminal. Click OK. Now, if we go to this toolkit and select the antenna design, okay, sorry for the inconvenience, but I forgot these steps. Uh, if you up to SIW antenna, if you have any query, we can solve that, and I will have to check this antenna array in instrument version. So, okay, I forgot this step. What we can do, we can right click here and go to create array. We need to right click on this design, then go to create array, select the vectors lattice pair 1 and lattice pair 2. These are the two lattice pair that we have earlier selected. Click apply. Now we have select we can select the size like 4 by 4, 4 by 4, click apply, then click on the active cells and all the elements we are making them active, and go to post processing cell and click apply. Now click now analyze all. So the size is very huge, that is why it is taking some time. So I will just cancel about this one. Now right click again and this result is not available. My chapter says, if we go to this one, let us try this again. We have selected this patch antenna. Then we go to this and remove the padding. Now in this design, we remove this radiation box, radiation boundary, select this object, right click, and go to boundaries, create coupled boundaries, auto identify, select this XY, and this has created two lattice pairs. Now select this region, right click on this, and assign it a radiation boundary. On the bottom also, now go to simulate and analyze this cell. No, that's- Okay, sorry participants, I am not able to cover this one. Sarthak sir, if you can help, please.
Hello.
Yes, sir.
Yes, sir.
Sorry, Swati, the last topic I am not able to give demo right now.
No problem, sir. Sir, we will share. If you will say share the notes, then we can share the notes of this last topic. Or
Okay, so
something.
I will share that notes later. Okay.
Okay. Then I will forward to them in the canvas.
Okay. So if there are any questions regarding the SIW, you can ask.
Participants, you can please ask the question, as this is the last session of today's FDP. If you have any query on the hands-on or any suggestion, as he has a lot of experience in HFSS and antenna designing, you may please ask here. And if you want to say something, or then you can raise your hand, then I will make you up. I will unmute you. Is there any questions, participants? Sir, I think no more questions are there.
Okay.
And sir, truly speaking, for me also, this session was, all the hands-on session were very, very good, sir. And those who don't know about the HFSS, for the beginners also, they were able to understand from it. So on behalf of EICT Academy, sir, and MNIT Jaipur, really very much thank you for a wonderful hands-on sessions you have taken, sir.
Thank you, Swati, for the invitation.
Sir,
And it was
one participant is saying that I want to learn HFSS and CST simulation. Please suggest some tutorials for beginners.
okay. So on YouTube, there are very high quality tutorials nowadays. And if you will search for last 1 or 2 years, then there have been some YouTube channels. Also, they have some dedicated webinars also. CST every month, CST has scheduled 1 or 2 webinars. You can go and check out their website. HFSS also has added some YouTube channel or some tutorials on the YouTube channel. And in addition, you can go to helps, and when you have installed the HFSS, you will be finding this HFSS help PDF. This is very comprehensive PDF containing all the examples and steps. Okay. So it is around 5,000 pages. It is all the designs, all explanations are there. And one more thing that Swati, you asked me how to simulate and export these designs.
Yes, sir. Yes, sir.
So what we can do, we can select this model and go to this modeler and click on export. From here, sorry, you need to select the design. You can select these designs and go to modeler, export. You can export as OBJ files.
Okay.
That OBJ file you will be able to or later on in HFSS. Let us say a, okay. So now this 3D file will be saved here. So this is a 3D object file. You can import it directly in CST.
Okay, sir.
But
And sir,
there is one limitation. As we are exporting this, then later on you are not able to modify any dimension in there. Okay. So once you have completed this design and optimize all the parameters, then only export it and simulate it. And if still you want to change some parameters, then you will have to again export it and import in CSV.
okay, sir. And sir, while importing from CST to HFSS, do we need to head to draw the boundary box in the HFSS, or directly we can simulate from CST to HFSS?
From CST, in which model you are exporting, you are if you go here in modular, select import, then there are step or DFX files. So DFX file are 2D files, and you select this step file, or in HFSS there is a setting for 2D and 3D objects, right? So either you import from there, and once you have imported, then you have to add this region, okay? And if you are exporting from HFSS to CST, then delete the region first, okay? So uh, in while importing from CST to HFSS, you need to design your own region.
Okay, sir. Sir, Arul Ranjan has said that if you can share any handouts or notes in the canvas. Arul Ranjan, sir.
Okay. Hands-on session shared in YouTube. We can access anytime or any time. I this hands-on session shared in YouTube. So Sarthar sir has the answer for that.
Sir, the previous question from the above, Arul Ranjan, sir. has said.
Let me answer this. The as Muqaddar had said, there is a help guide in the HFSS and CST both. Okay, regarding the design files. So you can
Yes.
the participants can practice them, and all these sessions are already available on YouTube, and these links are shared on the canvas also, so the participants can access them at any time. There is no such handouts for hands-on sessions. You have to follow the procedure which is given in the help guides of those softwares. I guess I was able to answer the questions.
Participants, if you have any more questions, you can please ask. Sir, I think no more questions are there.
Okay.
So on behalf of EICT Academy and MNIT Jaipur, thank you very much, sir, for the wonderful session.
Okay. Thank you very much. Thank you, Sarthak sir, for inviting me.
Thank you, Muqaddar.
Okay. So I hope participants have learned something.
Yeah,
Thank you very much.
they would have got benefited a lot.
Thank you very much.
Thank you. So now we are concluding this FDP, and thank you to all the participants. So, Swati,
Yes, sir.
now we can close this sessions and we can conclude the FDP. Okay.
Yes, sir.
Yeah.
Thank you all. Thank you all the
If
participants.
someone is, I think someone is asking something. No. Okay. Now we can conclude it. Thank you.
Thank you, sir.
मैं कर दूं